Hello and welcome back to Physical Geology. I am Robert Lopez. Today I want to start off with Chapter 4, which is Igneous Rocks. And one of the things we should start off with is we know that magma is molten rock, right? And in order to melt common silicate rock, we need temperatures of 1200 to about 600 degrees centigrade. And really those depend on the chemistry of the rock, right? So we've already talked about mafic versus felsic. So usually mafic rocks would be on this higher end here, whereas felsic rocks will be on this lower end, right? And so like granites and rhyolites for felsic rocks, basalt and gabbro here for the mafic rocks. Now, obviously we need heat to melt these rocks. And so where's this heat coming from? Well, some of it is relic heat from when the planet formed, right? Remember some of that gravitational energy and frictional energy as the planet was undergoing the differentiation event produce heat. And so some of that heat is still around. In fact, your book mentions that for the first 700 million years or so, Earth might have been completely molten or largely molten, right? Remember, the first rocks formed around 4 billion years ago. So this is a time between about 4.57 to about 4.0 GA, right? So a billion years ago. And that's when our first rocks really start forming at about 4 billion years ago. The other important one here is radioactivity. We know that with radioactivity, one of the outcomes is heat, right? So not only are you changing the atom by changing the number of protons, but you're changing or giving off heat. Now, we'll look at the causes of melting, and they include decompression melting. And I'll talk later on about hydrous flux melting and some other types of melting. But before we talk about the types of melting, note that the planet is primarily solid, right? It's primarily solid because we know S waves travel through it. The only place where S waves do not travel is the outer core. We know that that's molten. There are some regions in the mantle and in the crust, magma chambers, where there is magma, but there are small regions. It's a small percentage. By far, most of the planet is going to be solid, right? It's only where it's going to be hot, but where that heat moves and how we move these hot rocks, that can lead to melting. In fact, that's this first one, this decompression melting. And we'll look at figure 4.3 in your textbook here, but the key thing about pressure prevents atoms from breaking free of the solid mineral crystals, right? So remember, that pressure is inhibiting that kinetic energy. Remember, the kinetic energy is a vibration of these molecules. If you get those molecules vibrating fast enough, they're going to tear away from each other and slide by each other to make liquid, right? So even though we may have very high temperatures within the Earth, we're solid because of this pressure, right? And so this decompression melting occurs at divergent boundaries, mantle plumes, hotspots like Hawaii, and at rifts like the East African rifts. Now, so if we look at this figure 4.3 in your textbook, this is what it's referring to, right? So there's a few things I want to point out here, though, and this will be important for later on. Note that there's this line over here, this dashed line called a liquidus. And the liquidus is a line where if you cross it to higher temperatures, you're going to have 100% liquid. Think of this as 100% magma over here. And then over here, there's another line called a solidus. And the solidus is a line that if you're to the left of that solidus, that means everything to the left over here is 100% solid rock. 100% solid rock. So the region between the solidus and the liquidus, and what your book doesn't point out here, this region is called a partial melt. Rock is melting anywhere from 2% to 30% of that source rock is melting. And usually the source rock, really what these liquidus and solidus lines are, therefore the rock of the mantle. And we know that rock is peridotite, right? Peridotite. Important for two reasons. It's a rock of the mantle, and then it partially melts to produce basaltic mafic magmas, right? So when we look at that decompression melting, right? So an example here we have rock down here at about over 200 kilometers, right? If we could somehow move that rock like under Hawaii, it's solid rock, but it's moving up in one of these mantle plumes, when it crosses this solidus line, it's going to produce a partial melt. This is also true for mid-oceanic ridges. Mid-oceanic ridges, you know, here's a crust, 100 kilometers would be down here. So we're really down here, maybe about 30 kilometers under a mid-oceanic ridge. So if we're down here around 30 kilometers under a mid-oceanic ridge, and we move that rock up to shallow levels, we're going to cross that line and we're going to produce a partial melt. And that's how we get magmas at these mid-oceanic ridges, right? So the other one that we have here is this idea of melting as a result of adding volatiles, right? And that's what I call hydrous flux melting. And hydrous flux melting, mostly I'm talking about water, but carbon dioxide is another important one. And remember, volatiles are usually gases. They can escape easily from the magma, and when they escape, they turn into a gas. And these volatiles can help break the chemical bonds, and they lower the melting temperatures of magma. In fact, they lower those freezing points. And the analogy here is like salt on ice. When you put salt on ice, it lowers the freezing point. In other words, instead of ice freezing or melting at 0 degrees centigrade, it's going to melt or freeze at temperatures below that. So you don't need as much heat. So the key thing about the volatiles is, in terms of producing magma or partial melt, is that you don't need as much heat because you're lowering that freezing point, you're lowering that melting point. And in fact, the other point I make out here is note that a magma's freezing point is the same thing as a magma's crystallization point. Really, the temperature. If you think about ice, when you freeze water, water freezes at 0, right? So let's say you have a block of ice. To melt that ice, that block of ice will start melting also at 0 degrees centigrade, right? So 0 degrees centigrade is both the freezing point and the crystallization point for water, right? So that's really the same thing. And one of the tutorials we'll do this week will emphasize that point, right? Now, so we're lowering this, and so where does this happen? This mostly happens at subduction zones, right? Subduction zones. So your book also has a figure here. It's figure 4.4 in your textbook here. And so note that in a subduction zone, usually this is happening at about 100 kilometers beneath the in the subduction zone. And so remember, this ocean lithosphere is hydrated. It has volatiles in it. It's been at a mid-oceanic ridge where hydrothermal circulation has added water to the ocean lithosphere. That water is trapped in mineral grains. As the lithosphere goes down into the subduction zone at the pressures of about 100 kilometers, these volatiles are released, right? And the overlying asthenosphere, in some cases it could be mantle-peridotite, will melt. And these produce, because remember, you're lowering that melting point. And later on in another video, I'm going to show you how this hydrous flux melting occurs, right? So remember, in fact, even your book calls it flux melting, but I add the word hydrous to emphasize the water. And then this produces, remember the volcanic arc, the arc volcanoes. This is, in this example, this is like Mount Shasta. This is the origin of Mount Shasta. And so this is an ocean to continent magmatic arc, but if you were off of Japan, you would have an ocean trench, and then volcanic islands, and you would have an island arc there. Now, let's keep going here. The next point here is melting as a result of heat transfer or conduction, right? So remember, conduction is you have something very hot, like a hot pot, and you put it on a plastic countertop, right? It's going to melt that countertop just by the transfer of heat by conduction, right? And so the rising magma may melt surrounding country rock, or that, in fact, your book, that's another point I want to make here, is that your book uses the word wall rock. I often use the word country rock, and that country rock is basically the if we have existing strata here, older rock, right? And then through this, we're going to have an intrusion of magma, right? So this is going to be new magma that comes in here. So this is going to be eventually the igneous rock. So all the rock around here is the old country rock, right? And so that old country rock surrounds that new intrusion, the new magma body, right? And so your book calls this country rock, it calls it wall rock, only because it occurs along the walls of the magma chamber, right? Now, in fact, there is another figure, also figure 4-4 in your textbook, that kind of shows this example here. Here we have basaltic magma, mafic magma, pools in the crust. In fact, I also call this, is another word I want you to know. The word I use here is called underplating. Underplating. And all that means is this basalt magma pools under a tectonic plate. It pools under a tectonic plate. And remember, this stuff is hot. This is at 1200 degrees centigrade, right? It's very hot. In fact, it's going to be greater than that. Something hotter than 1200 degrees centigrade. So those high temperatures, well, that's plenty high to melt this crust. This crust usually melts around 900 degrees centigrade. 900 to about 1000 degrees centigrade. Depends on, again, on the composition, degrees centigrade. So that's plenty of heat to melt the surrounding rock. So just this rock being adjacent to this, being underplated by conduction, you're melting the surrounding country rock to produce secondary magmas here, right? Melting of crust occurs here, and then we make these partial melts of the country rock there. And in fact, here it looks like we're making rhyolitic magma. I'll talk more about this later on. Why different types of magma? There's ultramafic, mafic, intermediate, felsic. I use the words rhyolitic. I use the word andesitic, basaltic. Well, really, they refer to those compositional terms that we talked about already. So the difference is there's several reasons. One is we could have a different source rock, right? Another one, these source rocks are undergoing partial melting, maybe to different degrees. We may be assimilating country rock, right? Wall rock. We may be mixing magmas from two different sources, right? And so when we go back to this source rock, so remember the source rock never melts completely, right? It never melts completely. You only get a partial melt. And in fact, note that it's anywhere from 2 to 30% for that partial melt. And one thing is that the partial melt will always be more felsic in composition than the source rock. So if you partially melted a gabbro, which is a mafic rock, then you'd produce an andesitic magma, which is intermediate, right? If you partially melted an intermediate rock like a diorite, then you'd produce a rhyolitic rock, something that's more felsic, right? So that's a felsic rock there. So again, looking at these partial melts are always more felsic than the original source rock, right? Because remember, when we melt peridotite, remember peridotite is ultramafic. It's ultramafic. When you partially melt this, we produce mafic rock. And that mafic rock or mafic magma is basaltic or basalt. So that's kind of the clue right there. It's always going to be more felsic or less mafic than the source rock. Other things that may happen as a magma is moving up through the crust, some of the wall rock or country rock may stope or fall into the magma chamber and be completely melted and assimilated into that new magma, which causes the chemistry of that magma to change. And then again, you can have magmas coming from two different sources, and these two different magmas may recombine in one magma chamber, and the mixing of those two magmas will produce a completely different type of rock chemistry.